So for number 2, y'all, we have x squared minus 4 over x squared plus 3x plus 2. This is our lesson example problem number 2. I've got to find all the necessary information to sketch the graph. That's going to include horizontal asymptotes, vertical asymptotes, x-intercepts, y-intercepts, holes. And then, I'm interested in what the domain is. The way I'll ask questions on this on the exam, because these problems take, 3 or 4 or 5 minutes to do it. I can't give you an exam problem that takes 5 minutes if we're taking an exam in a regular class period. So what I might ask you on an exam question for this might just be, what is the domain of this rational function? Right? Where are the holes of this rational function? What's the horizontal asymptote of this rational function? Just one little piece of the puzzle. Okay?
Skip straight to that?
Yeah. Oh, yeah. Yeah, you can go straight to apply the rule. So all of the stuff that we're going to be doing, or most of the stuff that we're going to be doing, involves looking for zeros of the numerator, zeros of the denominator. So it's going to be very important to do a factorization of the numerator and denominator so we can see the zeros. All right, now we're prepared to answer our questions. What is the horizontal asymptote? What's the rule that applies here?
It's going to be 2.
It is y equals 1. Why is it y equals 1?
Because that would make the right x's equals 0.
No, it has nothing to do with the x's. The degree of the numerator and degree of the denominator are the same, so we use the leading coefficients. 1 over 1 is 1. All right? So just got to know the rules. All right? What about vertical asymptote? Do we have a vertical asymptote? X equals -1 is a vertical asymptote. Right? It is a vertical asymptote because it only makes the denominator equal to 0. All right. What about holes? Do we have any holes? Hole at x equals -2 because x equals -2 makes numerator and denominator equal to 0. Okay. Now I'm going to show you how to actually fill in the hole. When we defined what holes were, we defined them as removable discontinuities. So I can take this x plus 2 over x plus 2, and it can go away. Right? We can cancel that out. And that leaves us with a simplified version of this function is just x minus 2 over x plus 1. So now I have an expression that I can take the whole value and plug it into it, right? The whole value of -2 plugged into that will give me -2 minus 2 over -2 plus 1. What does that give us? Positive 4. Did we do this yesterday? So the whole actually is -2, positive 4. There's a hole at -2, positive 4. You could go over here to your graph right now if you wanted to and put a big hole right there. There's an open circle in the graph at that point.
So you take the -2, you got that because the x plus 2 and x plus 2 cancel?
Yes. Yeah, so that's why it's called a removable discontinuity, because we can actually remove the problem. We can actually cancel out the 0 from the numerator and denominator. And then you have something left over that you can plug -2 into and find out exactly where the hole is. That's the point of discontinuity. It's a point discontinuity. Yes, Drew?
How do you determine the holes at x equals blank? Like, how do you determine what that number is?
Whatever value makes the numerator and denominator equal to 0. So when you have these shared factors, right, x plus 2 and x plus 2, if you have the same factor in the numerator and denominator, the root of that factor, which is -2, is a hole.
-2, is it going to be the opposite of that number?
Mm-hmm.
Opposite value? So if
right.
it's 4, it would be -4?
Mm-hmm. That's right. That's right. All right, y-intercept. What's the y-intercept? We're just, I'm not doing these things in any particular order. What's the y-intercept? X is 0, y is -2. So If all these x's are zeros,
How do you find the 4 in the hole?
y is equal to negative 2. We'll have to catch it another time, Drew. I don't want to back up that far. All this work down here was explaining how to find the 4 for the hole. You tuned out on that one. I'll make sure you're tuned in the next one we do that. Yes. Who was asking me a question? All right. What about X-intercepts? 2, 0. So the X-intercept comes from the values that only make the numerator 0, and that's going to be x minus 2. Okay, so x equals 2 is an X-intercept. Now, the only other question that I would ask you for this is the domain, right? What's the domain? The domain of a rational function is all real numbers except the values that make the denominator equal to 0. So all real numbers except negative 2 and negative 1. Any value that makes the denominator equal to 0. Wholes or asymptotes. Any kind of discontinuity is removed from the domain.
So it's negative 2 because of the hole.
That's correct. Yeah. All right, so now we're ready to sketch. And the way we sketch our graphs, again, from our notes yesterday, is start with the asymptotes. Y equals 1 is an asymptote, so y equals 1 is our horizontal asymptote. X equals negative 1 is a vertical asymptote.
So an asymptote basically resets the graph.
Yeah, it kind of, you could see it that way. It kind of slides the...
But it doesn't change the points.
I don't know how to answer that question because I'm not sure I understand the question.
Okay, so like basically it doesn't move the whole y-axis over 1 to where...
No.
Okay.
It gives us these sections, right? So now we have this region on either side of the graph. So let's look at y-intercept is negative 2. X-intercept is positive 2. So those two points give us a real good idea what the graph does in this little region of the graph. It does that. And then the hole up there tells me what it does on this side of the graph. So it goes from that hole, it's going to go up from there. It's going to come down and curve to this asymptote there. So that purple part is what the graph looks like.
So you can only have 1 point. It is okay to only have 1 point?
It is okay to only have 1 point, unless for some reason we need to find a second one. It can't cross a vertical asymptote, and it's going to obey the horizontal asymptote. Usually it won't cross it on a rational function. Sometimes it can, and we'll look at an example in just a minute where it actually does cross the oblique asymptote. Remember, the asymptote tells us what the function is going to look like as x gets really, really big. So when x is small, when x is these small values here in the middle, the function doesn't look as much like the asymptote. But as x gets bigger, it's going to collapse to the horizontal asymptote. Okay? Y'all all right with this? Next example. Numero trace.
We did this one.
We haven't done 3 yet. You might have done some work on it. You did some work on number 3?
I got the whole thing done, and I didn't know how to do it until this class period. So we did something.
All right. That's okay. We're not going to argue that. He did something, that's for sure.
I'm just saying,
Well
I'm
done.
still asking you questions because I'm still kind of clueless on this.
Yeah, it's okay. You'll get there. Just bits and pieces, man. Bits and pieces, and cling to your notes. All right, let's start this one by factoring everything, because we know that all of the factors in the numerator and denominator are going to be important, right? So if we take an x out of the top, we're going to have x times x squared minus 16, which is going to be x times x plus 4 times x minus 4. And in the bottom, I could take out negative 2x, right? Let's take out negative 2x, and that leaves us with x squared plus x minus 2 x squared plus x minus 2 factors as x plus 2 times x minus 1. So now we can see all of the important things, all the factors of the numerator and denominator, and from the factors we can find all the roots, zeros, X-intercepts, points of discontinuity, holes, vertical asymptotes. Everything comes from those factors. All righty? So let's do this a little bit more methodically than we did the last one. Let's find the horizontal asymptote first.
So make the numerator equal 0?
Nope.
Make the whole equation 0?
Hey, the rule from your notes, horizontal asymptotes is based on the degree of the numerator denominator. In this case, the degrees are the same, right? So the horizontal asymptote is going to be y equals the leading coefficients of the numerator and denominator. What's the leading coefficient of the numerator?
1/2.
1. The leading coefficient of the denominator is -2. So 1 over -2 is -1/2. That's my horizontal asymptote. Okay, vertical asymptote. This one has 2 vertical asymptotes. Vertical asymptotes are values that make only the denominator equal to 0. So what are those 2 values going to be?
-2 and +1.
X equals -2, x equals +1. 2 vertical asymptotes. Okay.
And the whole would make the whole thing.
So where's the whole? The whole is a value that makes numerator and denominator equal to 0. We have a whole at x equals 0. There's only one value that makes numerator and denominator equal to 0. It's this factor right there. It's the only shared factor between the numerator and denominator.
I just asked you this. How do you determine, because the last problem, it was at x equals -2, and this one is 0. You determine that from x over x?
Shared factors. The shared factor is x. What's the root of x? 0. Okay. So now we can actually fill in the hole. Let's go back to this. So Drew, this is the part that you were confused about last time. To fill in the hole, you would actually cancel out those x factors, right? And what's that going to give us? That's going to give us x plus 4 times x minus 4 over